Hello, Assalamualaikum and good morning. Assalamualaikum and good morning. My name is Afif Muzuddin Bizulkifli. I'm a student of PhD on the Faculty of Computing Informatics, SPI, and this is my PhD research for RMC presentation. It is a structural-based visual decomposition of neural network decision pathways, a framework for enhanced model interpretability. Our online pages of my online pages of previous chapters. We have introduction, the black box problem, the goal of XAI, limitation of current XAI, the novel approach used in this research, the research objective, the core technical features of the research, the Gantt chart, which is the research timeline, also the conclusion. Introduction. The core goal is to develop a structuralizer-based neural network interpretability (SPNNI) framework that translates complex, deep neural network (DNN) operation into visually clear and interpretable representation. The focus area is on explainable artificial intelligence, which is SAI, in short, and DNN interpretability. The challenge, the black box problem. It is a deep neural network, a highly complex system. Usually have multiple layers, so therefore it often referred as black box because humans can easily understand how the internal decision making process. So why this matters? Because this complexity limits trust and acceptance. Lack of transparency prevents the widespread use of AI in high risk applications such as medical diagnosis, insurance, and financial services. This is high stake industries. Now, the current reputation. The current reputation is we need to because current visualization approaches often fail because to scale effectively, meaning that they can usually only use for small problem with minimal data. However, with modern models with billions of parameters, features, these visualization techniques cannot are able to serve our needs. The goal of SAI is because it is a field dedicated to making machine learning more transparent and understandable. We need to aim to increase user trust and comprehension. So this process will convert the opaque black box into a form that human can digest. So it is important to have transparency because it involves ensuring the internal mechanism of AI models are clear to promote trust and accountability. Because in the end, humans are the ones making the decision. Limitation of current SAI tools, which is called the post hoc explanation. Post hoc explanation is mainly used for SAI methods such as shape and line, which are post hoc, mean they generate explanation after the model has been trained. So this limits because generally is affected by the specific machine learning model used. So sometimes they can produce misleading results if the input features are highly related, meaning they have large relativity between them. Line will also often use simple linear approximation. They approximate the value using to the non-linear complexity that is inherently have in the deep neural networks. So that's why there is need to standardize. Basically, access to standardized visual language leading to communication barriers between technical experts and regulators. So this is important because having standard language can promote more discussion. The gap. To solve the visualization and transparency of gap is by adapting visualization principle from software engineering, which is our expression, which is the structuralizer architectural visualization approach, which uses C4 model principles to represent neural networks. The structuralizer provide language, DSL, domain-specific language, for generating expressive architecture diagram as code. Why C4? Because this model uses hierarchical decomposition to simplify complex systems and is widely used for creating consistent, easy to understand software diagrams. Our research objective 1 is design a hierarchical visual decomposition framework by adapting structuralized C4 model principle to neural network architecture. The visual grammar is the first step because it involves defining a formalized visual grammar and a complete taxonomy, a structure catalog for neural network components and the architectural pattern. There are 4 levels of abstraction in the C4 models. We define the NN interpretation across 4 increasing levels of details, similar to C4 model. Level 1 is context, purpose and data flow. Level 4 is code. And then from level 1 context to level purpose and data flow to level 4 code, which is individual neurons, weights, and activation function. Objective 2, we need to develop automated tools for extracting, analyzing, and visualizing neural network decision pathways. So the technology that we use is a functional software prototype will be implemented using Python, integrate various machine learning frameworks like TensorFlow and PyTorch. Visualization will leverage tools like Plotly. For so it's important to separate the models and the framework because the framework ensures separation of the model from the visualization process to maintain the model's integrity and reduce vulnerabilities of the model itself. Objective 3, how to validate and evaluate the frameworks. So validate framework using empirical studies. We need to adopt a design science research approach to develop and evaluate this innovative artifact. We need to conduct a between-subject experimental design comparing our SBN and I framework against baseline interpretability models, methods, and quantity measure. We need to measure user understanding using metrics such as task completion times, comprehension accuracy, and analyze viewing patterns using eye tracking data. This can be used with, for example, this laser pointer. If we move, people are more likely to follow it. So this is a simple eye tracking data that can be used to measure the effectiveness of our framework. Real world application. To demonstrate the framework, the practicality through case studies in computer vision, NLP, and medical diagnosis. Healthcare and medical, the system can assist physicians and common AI users in understanding complex diagnostics model, which is crucial for fostering trust and informed decisions in clinical settings. Regulatory compliance, the framework also provides sophisticated evidence-based visualization to support AI auditing and comprehensive model analysis, helping regulators develop the evidence-based policies. The core technical features, which is a structure-based interpretability, we need to have a decision pathway and flow visualization. We will map the DNN features using structure-64 model principles, which is the context, containers, and components, to provide a hierarchical view of the model from level 1 to level 3. We want to visualize the internal logic, which you need to have a flow. Our implementation focus on mapping the network flow via fault propagation tracing using flow-based visualization. Also need to have feature importance and interaction. We need to have attribution method with techniques like layer-wise relevance propagation and attention visualization for weight embedding. Each node have weights and visualization involved will pass with highlighting to emphasize active computational routes, identify critical neurons for attention weight using attention weights. Feature interaction mapping, which is specifically tracks how inputs combine to influence decision, generating importance scoring based on activation methods and gradients. You need to have input specific, which is causal analysis, which is a counterfactual capability. These features will perform input-specific analysis by showing pathways tracking based on specific input examples. This is a what-if scenarios. It will enable comparative analysis across different types of inputs, and support the generation of counterfactual explanation. It shows how minimum changes needed to input to alter the model's prediction. This will help, for example, if we want to achieve a certain outcome, what are the inputs that we need to change, or what are the parameters that we need to have before we achieve that outcome. So this what if scenario helps us for in this achieving this analysis. So our research timeline, concept, we have 4 semesters of over 2 years. Meaning the first semester is literature review, framework design, and basic structure visualization. Second semester is we need to prepare the decision pathways and also develop the interactive exploration tools and conduct the initial user studies. For the third semester, we need to extend to complex architecture, comprehensive evaluation studies, and also case studies in specific domains, specifically in the medical and the NLP process and also the finance. And so fourth semester, you need to integrate temporal aspects, have final evaluation, dissertation writing, and also the final publication needed for the studies. So, in conclusion, by adapting robust software architectural principles to DNN visualization, the SBNNI framework will offer a novel pathway toward enhanced model interpretability and transparency, moving beyond limitations of current post hoc explanation techniques. That is all for me. Thank you very much.